All right, guys, this is lesson 7.2.1, and it is about the sampling distribution of p hat, which basically is sample proportions, okay? So let's kind of work through this scenario together for a moment. Suppose a large bag of Reese's Pieces has 1,000 pieces. The manufacturer says that exactly 40% of the candies are orange. If we select a sample of 50 pieces, how many will be orange? Let X be the number of orange candies in the sample. Okay, if we were doing this in class together, I would actually have you guys work through this first page, 1 through 6, really, actually. I would have a stop sign here. I would have you guys do 1 through 6 together with your groups first, and then we would go over it. Obviously, we're not going to be collecting any data today since I'm not there, so we're going to use some sample data that I have. But using that sample data, I think that you guys actually can answer questions 1 through 6 with your groups. So I would encourage you to pause the video at this time and go ahead and answer questions 1 through 6 and see if it makes sense to you. And then watch this video, okay? So go ahead and pause it, do questions 1 through 6. And now we're going to go over 1 through 6. So it says, what type of probability distribution does X have? All right, we have learned about a few different probability distributions at this point. We've got normal, binomial, geometric, and uniform. In this particular case, this should be binomial. I'm noticing that I have a sample here, I have a percent. So we need to justify and actually check our conditions. So the first question is it binary? There are more than 2 colors. However, I am only interested in orange or not. So yes, this is binary. Now, technically, we are removing these Reese's Pieces and then not putting them back in the bag. So it's actually not independent, but we learned a rule that helps us know if something is independent. And that was the 10% condition. So is 50 less than 1/10 of 1,000, because the population was 1,000. And it is, because 1/10 of 1,000 is 100. So it is independent. We can consider it independent. N stands for the number of trials is fixed, which it is, it's 50. S stands for the probability of success stays the same. And because we can assume that they're independent, we're going to go with yes here. They told us that 40% of the candies were orange. So that means that this is binomial. All right, so this is the applet that we were going to use had I been there. Each person would have recorded how many orange candies they got from their sample. So just to kind of show you what we would have done, we would have gone to this applet. We need to change the probability to 0.4, and we're going to be drawing 50. The animation actually makes this kind of slow, but we'll just do one sample with the animation. And you can see that it is randomly selecting some Reese's Pieces, and right there I can see that there were 21 orange candies. So imagine that we did this multiple times. So we're going to pretend that everybody in the class did this. Here's an example of some ones people could have gotten. And here's a dot plot after many samples. Okay, so again, remember they were just counting the number of orange candies. In my case, I had 21. Here we go. Here are some other examples. So what does each of these dots represent? This is an important idea. One dot is one sample of 50 candies, counting, I don't like the way that's worded, I'm sorry. One dot is the number of oranges in one sample of 50 candies. So It's kind of important to think about this because we're going to be manipulating this. We want to think about like, what does the dot mean? So it was the number of orange candies in one sample out of 50. What is the mean and standard deviation? Well, reminder, this is binomial. You guys just took a test on this. And the formula for the binomial mean is n times p. So we would just do 50 times 0.4, and that gives us 20 candies. So we would anticipate on average, after doing many samples, that the average number of oranges out of 50 would be 20. And then the standard deviation formula was this one. So I'm going to plug those numbers in, and I get 3.46 candies. If you have your red pens out, I would say that like this formula and this formula would probably go in red if you don't already have them written down. What's the approximate shape of this sampling distribution? Explain and sketch it below. Okay, I kind of had a feeling people would forget about this, but there was a lesson that was not tested on our current test, or the most recent test, that had the normal approximation. Like there was a condition called the large count condition. So I'm going to write that in red off to the side here. And what the large counts condition told me was that if n times p was greater than or equal to 10 and n times 1 minus p, sorry, hold on, an extra 1 in there, was greater than or equal to 10, then I could assume the shape is approximately normal. So let's check it for our particular scenario. I've got 50 times 0.4, that is 20, and that is greater than or equal to 10. And then I have 50 times 0.6, which is going to be 30, because it's like the successes versus failures, basically. That also is greater than or equal to 10. So I can say that the shape of this distribution is going to be approximately normal. It asks you to sketch it. So reminder, when we are sketching our normal curve, we have the n with our mean and our standard deviation, and the mean goes in the middle. So honestly, everything from 1 through 6 was actually a review, and then we start getting into what this lesson is all about, the new stuff. So sorry, this looks weird, but that should say p hat. Instead of finding the number of candies that are orange, we're now going to find the proportion of candies that are orange. So we're looking at proportions. Using the samples from number 2, turn each number of orange candies into proportion of orange candies. So p hat is the symbol for a sample proportion. And the numbers that I had from number 2 had 14, 23. Well, basically what I'm going to be doing now is, because I'm turning it into a proportion, I'm just dividing it by 50. So I'm going to have 0.28 for the first one, for example. And then 23 out of 50 is going to give me 0.46, etc. So I end up with 0.28, 0.46, 0.36, 0.48, and 0.3. And all of these are p hats. Okay, so that's a p hat, that's a p hat, that's a p hat, because these all came from different samples, so they are all different sample proportions. And I'm going to go ahead and apologize if the sound is weird. I'm writing on the smart board and also talking into my computer, so that's probably, if it's weird, I'm sorry. What did you have to do to the number of orange candies to turn them into a proportion of orange candies? We had to divide by 50. Okay, not a trick question, just trying to be obvious. Okay, so here is the dot plot of proportion of orange candies. Notice if I compare this one to the other side, they look exactly the same, except for the x-axis. Now my x-axis is in proportions, and so I have decimals, but the shape and everything actually stayed exactly the same. So what does each dot represent? This time, instead of being the number of orange candies, it is the proportion of oranges in one sample of 50 candies. So instead of being the number, it is the proportion. This is important. Okay, here's the thing. I divided everything by 50. If we know our rules of transformations, which I know you know, that means that I should be able to just transform the new mean and then, transform the old mean and the new standard deviation. Means and standard deviations both get affected by division. So I would basically just be doing, so I'm going to say the mean of p hat. The original mean was 20, and now I'm going to divide it by 50. So that's going to give me 0.4. And the standard deviation of p hat, the original standard deviation was 3.46, but now I'm going to divide it by 50. And so that is going to be 0.0692. Now, here's what I would like you to add in red. This is a new formula. So the old formula for the mean was n times p, and now I'm dividing it by p. Nope, I'm not. Sorry, let me back up. I'm dividing it by n because n was the sample size. I divided it all by 50. So the mean of p hat is actually just equal to p. It means that like the more sample proportions I find, if I average them together, I'm actually just going to go, I'm going to get the true proportion. Okay, it makes it an unbiased estimator. Okay, so then the standard deviation, original formula looks like this. And I'm going to do dividing the whole thing by n. Okay, so I have to admit, if you look at their formula sheet, it actually doesn't look like this for standard deviation of p hat. What they did was they thought about if they wanted to have one big square root instead of a square root on just the top, it would be like this. Okay, so notice that those are equivalent things, right? And then they went ahead and simplified, they divided an n out. And so the sheet, the formula sheet, looks like this. Okay, so these are equivalent, this thing here at the top and this thing here at the bottom, but this is the way the formula sheet writes it, just because it looks a little bit neater than this one at the top. But either are fine. It's the binomial formula divided by n. Okay, so for approximate shape, we're basically looking at large counts again. I've already done that. Sorry, I'm like looking at it. I've already done large counts. But just a reminder, it's n times p has to be greater than or equal to 10, which it is. And in fact, what I just did is a no-no on the AP test. They actually want you to put the answer. So it'll be like, this equals 20, and 20 is greater than 10. Yay. Okay, and this equals 30, and 30 is greater than or equal to 10. Yay. So this is going to be approximately normal, but this time my mean is 0.4, and my standard deviation is 0.0692. So still normally distributed, but this time I have a different mean and a standard deviation. Okay, we know bags of Reese's Pieces contain exactly 40% that are orange. If we select a random sample of 50, what is the probability that the sample proportion will be 50% or greater? I said include a z-score in your calculation just because I didn't want y'all to forget about z-scores. We technically could just use normal CDF. Let's do a z-score real quick. So the value that I'm concerned about, like my borderline value, is 50%. That's 0.5. So remember how z-score is always value minus the mean divided by standard deviation? Okay, so my z-score is going to be 1.45. Okay, 0.5 is greater than the mean, and it did say 0.5 or greater. So I would be doing normal CDF to find that area. Let's go ahead and do that. Normal CDF. My lower bound is 0.5, my upper bound is infinity. My mean was 0.4 and my standard deviation was 0.0692. Okay, so I got 0.0742. And so the probability that we would get a sample proportion 50% or greater is about 7.4%. Now underneath the z-score formula, I would love for you to write this down. So let's think about what these things are in symbols. So 0.5, it's like, what's the probability that the sample proportion is 0.5? So the sample proportion symbol is p hat. 0.4 was my mean, which in this case, remember the mean is the same thing as p. We wrote that down up here when we were kind of rewriting the formulas, like the mean is the same thing as p. And then standard deviation was this new formula that we kind of derived. And so this is essentially our new z-score formula. I want to emphasize that it is still value minus the mean over standard deviation. Like that's still what it is. But I just have these different symbols in here now. The reason why I'm showing you that is because on the AP exam, they often will have multiple choice questions that have things that are like, which of the following is the z-score? And it'll look more like this. It'll have numbers plugged into this formula as opposed to like this. All right, so I need you to take out your notebooks to write down the big ideas, please. There are two main topics. And this is 7.2.1. Topic number 1 is the idea of a sampling distribution of p hat. Now, our example here was not a true sampling distribution of p hat because this is not all possible samples of size 50. Remember that a sampling distribution is all the possible sample size of 50. So I would say this is a simulated sampling distribution. Because we know how these distributions work, I know that if I found the true sampling distribution, that it would just look approximately normal. That's what the large counts tells me. So here are the things that are going to be true about sampling distributions of p hat. The shape is going to be approximately normal if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. That was called large counts. And maybe just mention that like n times p is the same thing as like your number of successes. And n times 1 minus p is your number of failures. So it's basically that your successes are greater than or equal to 10, and also your failures are greater than or equal to 10. The center, so you often hear me talking about distributions as like shape, center, spread. The center is the mean, which we kind of derived that formula, and it basically the mean of p hat is just p. Okay, then we have variability, which remember another word for variability is spread. And in this case, we're going to use standard deviation to measure our variability or our spread. And that is this formula. But I need to make a note that this formula is only true if the situation can be considered binomial. And so in order for it to be considered binomial, it has to be independent. And in order for it to be independent, or a way that you can check to see if it's independent is you can check the 10% condition. So if you are sampling without replacement, then you need to check the 10% condition. Okay, that was learning point number one. Learning target number one was like, how do we describe a sampling distribution? Learning target number two is about normal probabilities. And I feel like this is honestly just a review of what you already know about normal probabilities, but I'm going to apply it to proportions this time. So you'll have your normal curve, and then you'll have your mean of p hat and your standard deviation of p hat, and then your mean of p hat will go here. And just a reminder that mean of p hat is the same thing as p. If I'm asking you for like, what's the probability that we get a sample proportion of blah, 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 or less, then it'll look like this. So my p hat will be my boundary, and then I would shade to the left. And then just like I said before, the z-score is always value minus the mean divided by standard deviation. But in this case, my value is a p hat, my mean is p, and my standard deviation is this formula right here. Okay, so those are all of the big ideas. You should have everything you need right now to be able to do the check your understanding. And I would love for you to do the check your understanding and then actually check your answers. So in the folder, I'm going to put the answer key, and you can check your answers to it. And then you can go ahead and begin your homework. Thanks, guys.